Imagine a world so massive that it could swallow every other planet in the solar system and still be hungry. A world we've seen in the sky for thousands of years, bright and unblinking, a familiar point of light that has watched over every civilization that ever looked up. Now imagine this. For most of our scientific history, we thought we knew what lay at its centre: a heavy, solid core, a rocky heart, something dense and compact, like a buried planet trapped beneath an ocean of hydrogen. And then, one small spacecraft slipped into orbit around that giant world, listened carefully to its invisible signals, and quietly told us we were wrong. Today, we finally have a picture, indirect, mathematical, but astonishingly clear, of what Jupiter's core actually looks like. And it is stranger, softer, and more chaotic than anyone expected. To understand why that matters, and why it changes not just our view of Jupiter, but our understanding of how planets like it are born, we have to go back to a more human place, to a night sky, and to the first time someone realized that bright star wandering among the constellations was different. Jupiter has always had a kind of presence. If you've ever seen it with your own eyes, you know. It doesn't twinkle quite like the stars. It's steady, cream-colored. It has weight even from afar, as if your brain senses, without knowing the numbers, that there is a lot of mass behind that pale point of light. Ancient astronomers gave it many names. In Rome, it was Jupiter, king of the gods. In Greece, Zeus. In Babylonia, Marduk. Around the world, it became a symbol of authority, of protection, of storms and lightning. Nobody knew that, in reality, Jupiter was a world 11 times wider than Earth, with more than 300 times our planet's mass. That it owns most of the material left over from the Sun's birth that didn't end up in the star itself. But they sensed something powerful there, something large enough to earn myth. Today, we don't see Jupiter as a god. We see it as a key to understanding how giant planets form, a key to understanding the hundreds of hot Jupiters and cold Jupiters we've discovered orbiting distant stars, a key, in a very real sense, to explaining how a small rocky planet like Earth was even allowed to exist. But for all of our telescopes and equations and spacecraft, there was one question we simply could not answer. At the center of Jupiter, 600 million kilometers away, beneath clouds and storms and oceans of pressure, what is actually there? When you imagine the inside of Jupiter, your mind probably builds you a cross-section. You might picture cloud tops, then deeper clouds, then maybe an ocean of some exotic liquid, and then a solid core at the bottom. Something you could, in theory, stand on if you somehow survived the pressure and heat. For decades, that was basically the standard picture. A gas giant with a rocky core. But the truth turns out to be far more alien. And to understand why this question was so hard, we first have to step into a place we've never truly been, into Jupiter itself. Even sending a spacecraft there doesn't make this easy. In December of 1995, NASA's Galileo probe plunged into Jupiter's atmosphere. It sliced into the cloud tops at more than 170,000 kilometers per hour, the fastest entry of any human-made object into a planetary atmosphere. A heat shield burned away in a torrent of plasma, and then, for about 58 minutes, a small descent module sent back data as it fell. It measured wind speeds of over 700 kilometers per hour. It tasted the chemistry of Jupiter's upper layers. It showed us that the clouds we see from Earth are only the thinnest frosting on an incredibly deep atmosphere. But Galileo never came close to the core. It was crushed and vaporized at pressures of about 22 times Earth's sea level pressure. Impressive. Until you realize Jupiter's interior reaches pressures millions of times higher than that. The deepest it reached would barely count as a scratch on Jupiter's skin. We cannot send a probe to the core. Not yet, maybe not ever. The pressure at Jupiter's center is thought to be around 40 to 70 million times Earth's atmospheric pressure. Temperatures are probably in the range of 20,000 degrees Celsius or more. Under those conditions, rock stops behaving like rock. Hydrogen stops behaving like a gas. The word solid loses its meaning. So if we will never reach Jupiter's core directly, how can we possibly know what it looks like? The answer is the same trick doctors use on your body and geophysicists use on Earth. You don't have to cut something open to see inside it. You can listen to it. You can feel the way its gravity pulls. You can study how it rotates, how it vibrates, how its magnetic field twists and bends. You can build a model of its interior and ask, if Jupiter looked like this on the inside, would we see what we actually see on the outside? For decades, that was the game planetary scientists played. Long before Juno, missions like Pioneer 10 and 11, Voyager 1 and 2, and later Galileo flew past Jupiter or orbited it. They mapped its clouds, measured its magnetic field, took the first rough readings of its gravity. From those early measurements, scientists realized two things. First, Jupiter is not just a ball of gas. Deep inside, the enormous pressure squeezes hydrogen into an exotic state called metallic hydrogen. It's not metal in the way a steel bar is metal, but it conducts electricity and behaves more like a liquid metal than a familiar gas. Second, the way Jupiter's gravity tugs on passing spacecraft is not exactly what you'd expect from a simple, uniform sphere. It's a bit squashed, a bit lumpy, shaped in part by its rapid rotation. A day on Jupiter is only about 10 hours long, and by what's hidden beneath the clouds. These tiny deviations in the gravity field are like fingerprints of the planetary interior. But those early fingerprints were smudged. The data were not precise enough to give a sharp picture. So planetary scientists filled in the gaps with theory. They knew how materials like hydrogen and helium behave at extreme pressures and temperatures thanks to laboratory experiments and sophisticated calculations. They knew Jupiter's mass, size, and rotation rate. They also knew something about how planets form. The most widely accepted idea for giant planet formation is called core accretion. In this story, a growing baby planet starts as a clump of rock and ice, maybe 5 to 10 times the mass of Earth. Once it gets big enough, its gravity becomes strong enough to pull in huge amounts of hydrogen and helium gas from the disk of material that surrounds the young sun. If this is how Jupiter formed, then there should be a core of heavy elements buried deep inside. Rock, metals, ices. That heavy core would be surrounded by a massive envelope of mostly hydrogen and helium. And for a long time, that picture seemed to fit. Many models assumed a core of perhaps 10 to 20 Earth masses compressed into a relatively small dense sphere, maybe 10 or 20% of Jupiter's radius. But there was a problem. When scientists adjusted their models, changing the size of the core, the exact composition of the envelope, or how heat moved through Jupiter, they found something unnerving. Very different interiors could produce almost the same observable gravity and magnetic fields. If you imagined Jupiter with a big, distinct rocky core, it could fit the data. If you imagined Jupiter with a smaller core, or even no solid core at all, just a gradual increase in heavy elements toward the center, that also somehow fit the data. We had a handful of clues. We had early measurements of Jupiter's gravity. We had basic chemistry from the Galileo probe's brief dive. And we had our theories of planet formation and high-pressure physics. But inside that giant, the central region remained, in a very literal sense, unknowable. Some scientists argued for a clear, compact core. Others suspected a mixed, blurred interior. One planetary scientist I'll call Dr. Maya Chen once described it this way to a student. Jupiter is like a locked safe. We can weigh it, we can shake it a little, but we couldn't, until recently, feel exactly how the contents were arranged. To unlock that safe, we needed a mission built for one purpose: to feel Jupiter's gravity and magnetic field in exquisite detail from an orbit no spacecraft had ever flown before. We needed to fly over the poles. In 2011, NASA launched the Juno spacecraft. Unlike the earlier missions that skimmed by Jupiter or orbited in wide equatorial tracks, Juno was designed to dive repeatedly over the planet's north and south poles in a long looping elliptical orbit. At its closest approach, Juno would pass just a few thousand kilometers above the cloud tops, closer than many Earth-orbiting satellites are to our own planet. From that vantage point, it would do three crucial things. First, it would map Jupiter's gravity field with unprecedented precision by tracking tiny changes in Juno's speed as the planet tugged on it. Second, it would map Jupiter's magnetic field, which is generated deep inside the planet, probably near the region where hydrogen turns metallic. That magnetic map would add another layer of information about what's happening in the unseen depths. Third, it would peer beneath the clouds using microwave instruments, giving us a sense of how material like ammonia and water is distributed down through the upper atmosphere. That, in turn, would give clues to how Jupiter formed and how its interior convects and mixes. But for the question of the core, the gravity field was the most important. You can think of Juno as a kind of test particle, falling through Jupiter's gravitational embrace again and again, each time on a slightly different path. By listening to the radio signals between Juno and Earth, scientists could measure its speed changes to better than a millimeter per second. That's about as fast as an ant walks. From Earth, more than 500 million kilometers away, we were watching Jupiter tug on a robot and noticing when that tug sped it up or slowed it down by almost nothing. Those tiny changes encode the shape of Jupiter's gravity field, and the shape of that field encodes the shape and density of the interior. If Jupiter had a small, very dense rock and ice core, we'd expect one pattern of gravitational harmonics. Those are the mathematical terms that describe how the gravity deviates from a perfect sphere. If Jupiter had a big, puffy region in which heavy elements were mixed more gently into the hydrogen and helium, we'd expect another pattern. One Juno scientist compared it, in an interview, to trying to work out what's inside a spinning raw egg versus a hard-boiled egg without cracking it. If you spin them, they behave differently. The way the mass flows inside affects the way they move. Juno was, in essence, spinning Jupiter in our models and asking, which interior makes these measurements make sense? On July 4th, 2016, Juno fired its main engine and slipped into orbit around Jupiter. For a moment, the spacecraft passed behind the planet from Earth's perspective. Jupiter's bulk blocked radio contact. The mission team had to wait in silence, knowing that if anything had gone wrong, they would only find out after it was already too late. When Juno emerged and began to transmit again, the data told a simple story. The burn had worked. The spacecraft was in orbit. Over the months and years that followed, Juno would complete close flyby after close flyby, each time diving over a pole, shooting past within roughly 4,000 to 8,000 kilometers of the clouds and then spiraling far back out. Each pass was like another tap on the cosmic safe, another feel of the weight inside. At first, the results trickled in as numbers on a screen. Tiny shifts in Juno's radio frequency, Doppler shifts caused by speed changes as subtle as a gentle breath. On their own, those numbers mean almost nothing. But when scientists began to stitch them together, something unexpected began to emerge. The gravity field wasn't matching the classic picture. It hinted at something else. Not a small, compact, solid core, but something expanded, something diffuse, something that would force us to redraw the inside of the largest planet in our solar system. And it would raise a haunting question. What could possibly have happened billions of years ago to blur the heart of a world like Jupiter? When the first detailed gravity data from Juno came back, it didn't arrive with fireworks. It came as a set of numbers, coefficients, tiny deviations in Jupiter's pull measured to absurd precision. Most of us will never see those numbers directly, but in the offices and late-night home setups of planetary scientists around the world, they appeared on screens like a new dialect of a very old language. J2, J4, J6, the so-called gravitational harmonics. If a planet were a perfect sphere of perfectly uniform material, those harmonics would be very simple, smooth, predictable. But Jupiter, spinning once every 10 hours, swelling at the equator, sculpted by deep flows and layered materials, is not simple. Its gravity field is rich with structure, and that structure is the only way we can see into the hidden layers. One researcher, working with Juno's data, later described the moment as realizing that Jupiter wasn't playing the tune they'd expected. It was still in the same key, but some of the notes were shifted. To understand what that means, imagine Jupiter as an orchestra and its gravity field as the music it plays. The lowest harmonics, like J2, tell you about the broad strokes, how squashed the planet is, how much mass is concentrated toward the center versus the outer layers. Higher order harmonics, like J4, J6, J8, bring out the finer details. Is the interior symmetric? Are there flows or asymmetries? Is mass more spread out or tucked tightly inward? This is what Juno was listening to. And as scientists compared the music of Jupiter's gravity with different interior models, a pattern began to emerge. If you assumed a small, compact rock and ice core, like the kind we'd been drawing in textbooks for decades, you could match some of the data, but not all of it. Specifically, you ran into trouble with how well you could simultaneously fit both the lower and higher order gravity harmonics. If you tuned your models to match the bulk flattening of Jupiter, you'd end up with harmonics that were a little off from what Juno actually heard. If you forced the harmonics to fit, the implied structure of Jupiter's interior started to look odd. Heavy elements, the things we loosely call metals in astronomy. Oxygen, carbon, nitrogen, silicon, iron, and so on, weren't comfortably sitting in a tight ball at the center. They were spread out, not evenly throughout the whole planet, but in a broad, diffuse region extending outward from the core. Instead of a sharp boundary between a dense, solid heart and a lighter, gaseous envelope, the models that best fit Juno's data had something different. A gradient. A gradual increase in the fraction of heavy elements as you move inward, with no clean dividing line where you could point and say, "Here, this is the core. This is where it ends." One team, analyzing the data, came up with a picture where Jupiter's core could extend to nearly half the planet's radius. Not as a solid object, but as a fuzzy, diluted zone containing perhaps 10 to 20 times the mass of Earth in heavy elements, stirred and smeared into the surrounding hydrogen and helium. Another team, using slightly different assumptions, found similar things. In some models, the diluted region was a bit smaller, in others, a bit larger. But almost nobody, working carefully with the Juno data, was ending up with the old-fashioned picture of a neat, compact, sharply defined core. Planetary scientists are, by training, cautious people. They know how easy it is for a favored theory to seep into the way you interpret data. They argue about error bars and boundary conditions, about equations of state, how matter behaves at pressure and temperature regimes we can barely reproduce on Earth. And yet, across multiple independent groups, a consensus was forming. Jupiter's heart is not a clean, sharp stone. It's something more like a storm of elements, a hot, dense, partially mixed region where hydrogen acts like a liquid metal, and heavy elements are dissolved into it like salt in a boiling, pressurized sea. A fuzzy core. The phrase sounds almost cute, but the reality is anything but gentle. We're talking about a region millions of kilometers across, at temperatures a significant fraction of the sun's surface, under pressures unimaginably beyond anything on Earth. To really feel how strange that is, we need to zoom in on what matter is even doing down there. Near Jupiter's cloud tops, the world we see in photographs, hydrogen is a gas. It behaves, in many ways, like the air you're breathing right now, just far denser and under higher pressure. Go deeper, and the pressure builds. Tens, hundreds, thousands of times Earth's atmospheric pressure. Hydrogen molecules are squeezed closer and closer together. Eventually, the heat and pressure break them apart into individual atoms. Deeper still, those atoms are forced so tightly together that their electrons can move freely, like in a metal. At that point, hydrogen becomes what we call metallic hydrogen, a liquid that conducts electricity extremely well. It's believed that this metallic hydrogen layer, spinning and churning, is what powers Jupiter's enormous magnetic field. Somewhere in and around this metallic region is where the fuzzy core lives. It's not made of stone in the way you might picture the rocks under your feet. Even the so-called rocky materials behave like super hot, super compressed fluids or exotic solids that only exist at these extremes. If you could somehow teleport a block of Earth's granite into Jupiter's core, it wouldn't remain a block of granite for long. It would be crushed, heated, and chemically altered into something unrecognizably different. The heavy elements that make up Jupiter's core region, silicates, iron, water, ammonia, methane, and more complex compounds, are probably mixed into the metallic hydrogen in varying proportions. The Juno data suggest that this mixture is not uniform. There's likely a central region where heavy elements are most concentrated, but the transition from that region to the relatively lighter surroundings is gradual, not sharp. We're used to thinking in layers: crust, mantle, core. Clear boundaries. But inside Jupiter, those boundaries blur. And that blurring forces us to ask an even deeper question. How did it get this way? If Jupiter formed with a neat, heavy core that pulled in gas around it, something must have happened to smear that core out. One possible answer comes from the physics of convection and mixing. Inside a giant planet, heat tries to escape from the deep interior to space. One very efficient way it does that is through convection. Hot material rises, cooler material sinks, just like water boiling in a pot. Convection is a powerful mixer. If the interior of Jupiter has been convecting vigorously for billions of years, it can erode and stretch out an initially compact core. Heavy elements can get mixed upward. Lighter materials can get dragged downward. But there's a complication. Heavier elements tend to resist mixing. It takes energy to stir dense, metal-rich fluids into lighter hydrogen and helium. Under some conditions, the interior can settle into a state called layered convection or double diffusive convection, where mixing is partial, slowed down by thin, stable layers. In such a world, the core might gradually blur, but not disappear, leaving behind exactly the kind of fuzzy, extended region Juno's data hints at. Another possibility is more violent. In 2019, a study suggested that Jupiter's strange core could be the scar of a long-ago collision. In simulations, researchers took a young Jupiter and slammed into it a massive protoplanet, something perhaps 10 times the mass of Earth. If such a colossal impact happened early enough, when Jupiter's envelope was still forming and not yet fully settled, the incoming body could plunge deep into the planet, smashing and mixing the original core, injecting heavy elements throughout a big central region. The result, after a few million years of settling, looks a lot like a fuzzy core. This scenario is dramatic, but not implausible. In the early solar system, collisions were the rule, not the exception. Earth itself was likely struck by a Mars-sized body, Theia, in a collision that helped create the Moon. Why couldn't Jupiter have had its own catastrophic encounter? Some scientists are drawn to this story. It has a kind of narrative elegance, a giant world with a wounded heart, forever shaped by one titanic impact. Others prefer more conservative explanations: long-term mixing, slow erosion, the subtle games of heat and composition. At the moment, the data doesn't let us choose with complete confidence. What Juno has given us is less a photograph and more a constraint. Jupiter's interior must behave in a way that produces the gravity field we've now measured. Many detailed models, using different physical assumptions, point toward a diluted core, rich in heavy elements, extending perhaps 30 to 50% of the planet's radius. Whether that fuzziness is mostly the product of a dramatic collision, slow internal churning, or some mixture of the two remains an open question. But even with uncertainty, one thing is clear: The picture of Jupiter as a simple gas ball with a compact rocky seed at the center is gone. It has been replaced by something far more complex and far more revealing, because the story doesn't end with the core itself. To extract the core's properties from Juno's data, scientists had to also understand something else Juno discovered: the depth and structure of Jupiter's powerful jet streams. From Earth, through a backyard telescope, Jupiter's atmosphere appears as alternating bands of lighter and darker clouds, zones and belts. These bands are the visible tops of jet streams that circle the planet at hundreds of kilometers per hour. Before Juno, it wasn't clear how deep those jets went. Were they shallow features confined to a thin weather layer? Or did they extend far into the interior, dragging mass with them, altering the gravity field? Juno's gravity measurements, combined with careful modelling, suggested that those jets reached thousands of kilometres below the cloud tops. Not all the way to the core, but deep enough to matter. That means the gravity field detected by Juno is a combination of two things: the permanent, underlying mass distribution of Jupiter's interior and the slightly shifting mass of these deep winds. To see the core, you have to subtract the wind. Scientists like Dr. Aaron Patel, a specialist in planetary fluid dynamics, spent years refining models of how those deep flows would influence the gravity harmonics. They worked closely with colleagues who focused on the static interior, iterating back and forth. If your model of the winds was off, your inference about the core would be off. If your core model was unrealistic, your wind model wouldn't be able to reproduce the observations either. This dance between atmosphere and interior is what ultimately gave confidence that the diluted core picture was real. Different approaches, different codes, and different scientific cultures converged on a similar result. Meanwhile, Juno's other instruments were painting their own portraits of this world. The microwave radiometer showed that ammonia, a key ingredient in Jupiter's atmosphere, is not evenly mixed. It forms complex structures stretching deep below storms and bands. Juno's magnetometers revealed a magnetic field with unexpected patches and anomalies, like the so-called Great Blue Spot, a concentrated region of intense magnetism near the equator. That, too, hints at a non-uniform interior with flows and structures near the boundary of metallic hydrogen. The visible camera, JunoCam, originally included mostly for public outreach, delivered jaw-dropping images of the poles. Lattices of enormous cyclones, each larger than a continent on Earth, swirling in arrangements that are as mathematically fascinating as they are beautiful. All of these things, jets, storms, ammonia plumes, magnetic scars, are, in a sense, surface symptoms of a deeper reality. Jupiter is not a static ball of gas neatly layered above a dead, dense core. It is an active, evolving, dynamically complex world, whose interior is in constant negotiation with its atmosphere, with its magnetic field, with the leftover heat from its formation. In this light, the fuzzy core is not an oddity. It's a natural outcome of a planet that has been restless for 4.5 billion years. And suddenly, that ancient point of light in the night sky, which once stood for a god or a symbol of unchanging authority, reveals itself as something more chaotic, more fragile in its own way, more alive. Our mental map of Jupiter has been rewritten. Where we once imagined a clear boundary between core and mantle, we now see a continuum. Where we pictured a neatly separated heavy heart and a light gaseous shell, we now have a blurred interior full of gradients. And that change doesn't just apply to Jupiter. It ripples out into how we think about every giant planet we've ever found across the galaxy. Because once you learn to read the music of one giant's gravity field, you can start to hear echoes of that tune in the others. If the largest planet in our own solar system hides a diluted, extended core, what does that say about the hot Jupiters orbiting other stars in just a few days, roasted by intense starlight? What about the gas giants around distant suns that have likely endured powerful tides, strong irradiation, and maybe their own ancient collisions? One mysterious interior, suddenly brought into sharper focus by a spacecraft we built and flung across the void, becomes a Rosetta Stone for thousands of worlds we may never visit. And at the same time, it forces us to revisit a surprisingly simple question. How do planets actually begin? To go deeper into that question, and to see what Jupiter's revealed core tells us about the origin of our entire planetary system, we have to step back, not just from Jupiter, but from the solar system as a whole, and look at it the way the universe does, from the outside.